Now we've already looked at how we can take a binomial distribution and take a Poisson approximation to it, and this video is about taking a binomial distribution and using a normal approximation. Later on we'll be looking at taking a Poisson and approximating that by a normal. But this video we're looking at today is about going from a binomial to a normal. So let's consider a binomial distribution with 20 trials and the probability of success being 0.5. We can work out the probability of each of the numbers from 0 to 20 and we'll get these probabilities. Notice the symmetry of this distribution, and in fact it looks very much like the normal distribution which we've seen before. So the key elements are shown here. For a binomial distribution, the mean is mu, which is n times p, and the variance is sigma squared, where sigma squared is np1 minus p. So if we take a binomial distribution, we can approximate it by a normal distribution, mu sigma squared, where that's what mu is and that's what sigma squared is. However, it's not always possible to take a normal approximation. Let's have a look at a slightly different distribution. Here we've got the binomial distribution, 20 trials, and the probability of success is 0.1. That's what the probabilities look like. And if we take if we draw a smooth curve over that, it looks nothing like a normal distribution. So there are situations whereby we cannot take a normal approximation. So in which situations is it okay, and in which situations is it not okay? And here's the answer to that question. The approximation is valid when np is greater than 5 and n1 minus p is also greater than 5. So in the previous example we had 20 and 0.1. So n is 20, p is 0.1. So np is 20 times 0.1, which is 2, and n1 minus p is 20 times 0.9, which is 18. So although that bit is okay, this bit isn't. So the facts to remember are it's valid when np is greater than 5 and n1 minus p is also greater than 5. Now let's look at this example. We've got a binomial distribution with 20 trials and probability of success 0.5. And what's the probability that x equals 8? Now if we didn't make an approximation, we could simply say that this is 20c8, 0.5 to the power 8, 0.5 to the power 12. And this works out to be 0.120 to 3 sig figs. So that's probably the most straightforward way of doing it. But let's see if we can use a normal approximation. So we've got n is 20, we've got p is 0.5, so np is 10, n1 minus p is also 10, so we can use a normal approximation. There we go, because np is greater than 5, n1 minus p is greater than 5. So np is 10, so the mean is 10, and np1 minus p is 20 times 0.5 times 0.5, which is 5. So we can say that y is a normal approximation with mean 10 and variance 5. And now we come across something that's incredibly important, and I'll start off by showing you what the problem is. It seems that we want to know what's the probability that y equals 8, and from a normal distribution, the way we work out probabilities, we've got a mean there of 10, we've got a standard deviation of root 5, we want the probability that y equals 8. Now in a normal distribution, because normal distributions are for continuous data, what we want to know is what's the area of that line. Now that doesn't make any sense, you can't have an area of a line. And what we're doing here is we're using continuous data to approximate discrete data. the continuous data is in the normal distribution, the discrete data is in the binomial distribution. So the probability that y equals 8 is actually represented by the area there. So it's the area between 7.5 and 8.5. So to work out the probability that y equals 8, we need to find that area. So when we work out the probability that x equals 8 for the binomial distribution, what we're really saying is what's the probability of y being between 7.5 and 8.5. It's not possible to work out the area of a line, so it doesn't really matter whether that's got an equal sign in it or not. Obviously with discrete numbers the equal signs are important, but if we wrote that as the probability that 7.5 is less than y is less than 8.5, that would be exactly the same, because the probability is worked out by areas. So the difference between this line and that line is that we've excluded the equals bit. So we've excluded this area. It doesn't make any sense to talk about the area of a line. So excluding an area doesn't make any difference. So these two are the same. It's probably a good idea to get in the habit of writing this, but this bit isn't wrong. So let's standardise. So it's the mean was 10 and the standard deviation was √5. So we get that, and then we can work these numbers out. So we get minus 1.12 and minus 0.67. Because they're negative numbers, we've got to do 1 minus each number, and we get 0.12. Which is the same answer as we got a few minutes ago when we worked out the binomial probability directly. And in this example, working out the binomial probability exactly is the quickest way of doing it. But there are other situations where it's quicker to make a normal approximation. And here's an example. So we've got a binomial distribution, 200 events, probability of success is 0.75. What's the approximate value of x being between 140 and 155? So we could work out the probability of every number from 140 up to 154. Notice 154 because x is less than 155, so x could equal 154. So while it's discrete, it's important that we get the equal signs right. But obviously that's going to take a lot of time. We'll have to work out 15 different probabilities. So let's do a normal approximation. So we've got n is 200, we've got p is 0.75, we've got np is 200 times 0.75, we've got n times p is 200 times 0.25, that's 50. So both of those are bigger than 5, that's okay, so we can use a normal approximation. So the mean is n times p, that's 150. The variance np 1 minus p is 150 times 0.25, which is 37.5. So therefore we've got x is a binomial distribution, and so y is a normal distribution with mean 50 and variance 37.5. So it's worth thinking about exactly what these numbers are. X is any number between 140 and 155. So it can equal 140, but it can't equal 155. So they are the x numbers. So the y numbers, because we need to think about the continuity correction, the y numbers go from 139.5 to 154.5. That's because 139.5 and above will include 140, and there's an equal sign there, and 154 and below will not include 155 but will include 154. Now drawing this diagram is very helpful and avoids those expensive errors that can lead to you getting completely the wrong answer. So what we're after here is the probability that y is between 139.5 and 154.5. Now it's at this point it doesn't matter whether you put the equal sign or not. I always put them in, but that bit doesn't really matter because the probability that y equals 154.5 is 0. So it's important that we get this bit right here, it's important that we get this bit right here, and then we're working out y being between 154.5 and 139.5. So then we standardise, so it's 139.5 minus the mean divided by the standard deviation. These are now z numbers because we're standardised. It's 154.5 minus 150 over root 37.5. So that works out to be minus 1.71 and 0.73. And that works out, so we need the probability that x is less than 0.73 minus the probability that z is greater than minus 1.71. So that's 0.7673 minus, now this is a minus number here, it's 1 minus 0.9564. Remember your work from S1. And this works out to be 0.7237.